Okay, so resuming on where we left off, just a small modification about this is that for hashing, when we see we hash a value means we take a number and mod it by a prime number q. So which is why over here we have the number 5 mod 13 is equals to 5 in this case. And then now I see that I'll provide an example to show this. So generally M and M should be large and Q should be a large prime number. But in this example, we're just going to use a small value of M and a small prime number because it's easier to do the calculations. But the idea is still the same. Okay, so let's say if P is equals to this binary string and our text is going to be quite long. 110, then 01, 4 zeros, followed by 10110100. And then I'm just going to write here, in this case, remember M is the length of P, which is equals to 5. And we know that Q, in this case, it has to be a large prime number, but we just pick a small prime number to make it easier to calculate. And in this case, remember, we need to calculate the value, the hash value of this string of P once. And in this case, HP is equals to 5. Okay. And the value of this over here, we calculate it once, we should take theta of M time. And this value is equals to 6 mod 13. Mod 13, which will give us 6. So we know that HP is not equals to, we know that HT is not equals to HP. So that means we move on to the next window. Okay. And the next window, okay, I just put a bunch of dots here to represent the rest of the characters. Okay, this is the next window, which has to be of length 5. And over here, okay, remember that small t is equals to 12 cos A plus 4. But then we want HT, and HT is equals to 12 mod 13, which is equals to 12. And 12 is not equals to 5. You remember? So we move on to the next window. So the next window will be this over here. And T is equals to 25. And HT is equals to T mod 13, which is 25 mod 13, which is equals to 12. So 12 is still not equals to 5. Yeah, HT. Yeah, I just want to write it this way, it's easier. Yeah, so we move on to the next window. Okay, and then we'll basically just keep on doing this. Okay. Okay, so this will be 0, 0, 1, 1, 0, 0, 1, then 0, 0, dot, 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 dot. Yeah. Okay, for this over here, t is equals to 16 plus 2, so it's 18. ht is equals to 18 mod 13, which is equals to 5. And we know that, remember, hp is equals to 5. Okay, and in this case, ht is equal to hp. Now this one double equal sign. So we compare p and t. Yeah, so remember, if we go back to the previous slide, if you look at step 3 over here, when hp equals to ht, we compare the pattern with the text window. So the text window is over here, 10010. Okay, so how to compare? It will be like what we did for the brute force aka the naive algorithm, where in this case p is 00101 and our t in this case is our particular window in t in this case is 10010. So we just do one comparison only because here, let me just spread it out. 00101 10010. So it's obvious that when your one comparison is done, because there's a mismatch. If there weren't a mismatch between the first set of characters, then you do the second comparison and so on. Okay, so I'm not going to bore you with the rest of the comparisons, but okay, let's say I just put a bunch of dots here to show that we move on all the way until, actually, remember there's 00110, 0100, 0101. Dot, dot, dot. And then once we are at this window over here, we realize that ht equals to 5 mod 13, which is equals to 5. And then in this case, ht equals to hp, and we compare p and t, and we know that p is 00101, and that, okay, maybe I just put t prime here. T prime here means that specific window in t. Yeah, maybe I just put tw. Just put it with here tw. Maybe I just put it as lower strip. Yeah. tw is our specific window in t. In this case is 00101. And in this case, remember we compare the first set of characters it matches, second set it matches, third set it matches, fourth set it matches, and the fifth set it matches. Yeah, so in this case, there'll be 5 comparisons. And in this case, the number of comparisons is equals to m, which is why we stop this algorithm and say that we have found p within t. Okay. Yeah, but remember that whenever hp is equals, whenever ht is equals to hp, yeah, just put a double equal sign here. That whenever ht is equals to hp, and we compare p and t, remember that this comparison PNT is done using the naive algorithm. So in a way, compared to the naive algorithm, which executes for every single case, for this Rabin algorithm, we do use a bit of the naive algorithm, but only when HT is equals to HP, just that we need to compare PMT. So I just put here using similar logic, but it's not entirely the same code as a naive algorithm. But there is some similarity in comparing P and T in this case, whenever HT is equals to HP. Okay, and so now we are going to write the code for it. And remember how I said that the reason why we do the hashing is to prevent the buffer flow? Well, that means that during the code, we'll need to use some mod. Like we need to, okay, I'll just write it here. Hashing to prevent buffer overflow, which occurs when the number is too large. And it means we need to introduce modulo. We need to have modulo in our code, especially for all the intermediate steps. And these are some useful properties to know. The first one is x plus y mod q is equals to x mod q plus y mod q. Okay. Then the entire thing, we mod it by q. Okay, and the second one is xy mod q is equals to x mod q y mod q, and the entire thing mod q. So basically, we're just we're introducing more mod q's. And the last one is not really used as much as the first two, but it's just a useful thing to know is that whenever we've taken the modulo of a number once, applying it again doesn't make much difference. So let's say we take x mod q once is the same as taking x mod q, and then we mod q the result again. It'll be the same. So now is whenever we want to calculate HP, which is the hash value for the pattern, we'll need to call a function. Okay, so function to calculate HP. I suddenly thought of Harry Potter. So let me see whether I can just paste the code here. So just give me a second. It is the code here. And this is the code for reference. So I'll just put it here. Code without hashing or reference. So the whole idea is that we need to transform this code without hashing. Let me select my pencil. We need to transform this code without hashing into one that has hashing. So in order to convert it to the code over here, let me see what direction. Now I'll just get some indentation in here. It takes some time to convert this code that you see on the right to the one on the left. But the general idea is that we just want to introduce more modulo signs over here, because this will help to make the value smaller. It will make the intermediate value smaller, which helps to reduce like the size of aka the value of h, so that we can still store in the buffer without buffer flow. So I'll just write it over here. Sure. Oh, this is and if you want to know how to go from this version without hashing to this version with hashing code-wise, do let me know in the comments, because I can upload the documents for it, but it's quite long. Okay, then I'll just put an example here for you all to go through. Yeah, I mean, I won't go through it step by step because that will take some time as well, and I believe that you are able to go through this on your own. You can do it. And okay, so if I'm just going to shift this to the top right, then I erase this. If we look at the code over here, then this takes O or theta of 1, and this also takes theta of 1. Okay, so the overall time complexity is theta of 1 plus, again, number of iterations times the time complexity by iteration. I just put KC here. So it's equals to theta of 1 plus there are n minus 1 iterations times theta of 1, and all of this simplifies to theta of m. So this means that the numbers hp and ht can be converted in theta of m time. We'll leave stop here for now.